All right, let's just jump right in. We are surrounded by this invisible world of energy. There's this constant dance of heat moving through the very air we breathe. It's called radiative heat transfer, and believe me, it's a force that shapes pretty much everything, from the weather outside to the inside of a screaming rocket engine. So today we're going to make this invisible force visible.
And to get our heads around this, let's start with a really simple question. Why is our atmosphere like an invisible blanket? I mean, it feels like nothing, right? Like empty space. But it's the one thing that keeps our planet comfortably warm instead of being some frozen rock hurtling through space. The answer? Well, it all comes down to how this thin air plays with energy.
Okay, so check this out. It's all about a massive energy exchange. The sun, which is incredibly hot, blasts us with high-energy, shortwave radiation, mostly visible light. That light zips right through our atmosphere, no problem. Then, the much cooler Earth radiates that energy back out as lower-energy, long-wave infrared radiation. Now here's the kicker, the really crucial part. Some gases in our atmosphere let all that sun's energy in, but they don't let all of the Earth's heat out. They trap it. It's basically a one-way valve for heat.
So here's the game plan for this explainer. We're going to start with that invisible blanket. Then we'll meet the main character in this story, the participating medium. After that, we'll look at the 3 things radiation can do, figure out how we decode all the complex math behind it, and then see how this pops up in everything from rockets to our climate. And finally, we'll tackle the next frontier. What happens when you mix gases together?
So that invisible blanket, that's really what we're talking about when we say the greenhouse effect. Now, it's not a perfect metaphor, but it gets the main idea across. You've got gases like carbon dioxide and water vapor that act like a bouncer at a club. They let the high-energy solar radiation come right in, but when the Earth tries to send that energy back out as infrared heat, they block it at the door, absorbing it and sending it back down, keeping our planet warm enough for all of us. So to really get why certain gases are so good at trapping heat, we've got to zoom in, way in. We're going from the scale of the entire planet down to the nitty-gritty physics of the gas itself. Because we can't just think of it as empty space anymore. We have to see it for what it is, an active player in this whole energy game. And that brings us to this term, a participating medium. It's basically any gas that doesn't just let radiation pass through like it's not even there. No, it gets involved. Think of it like this. Radiation moving through a non-participating gas, that's like strolling down a totally empty hallway. Easy. But sending it through a participating medium, that's like trying to cross a packed dance floor. You're going to bump into things, get spun around, your path is going to change. So what's actually happening on that crowded dance floor? Well, when a little packet of radiation, a photon, runs into a gas molecule, there are really only 3 things that can go down. And these 3 interactions, they govern this entire process. First up, you've got absorption, and it's exactly what it sounds like. The gas molecules literally reach out, grab that incoming radiation, and absorb its energy. They basically eat it. That energy gets transferred from the radiation directly to the gas, which, you guessed it, heats it up. But here's the thing. It is absolutely a two-way street. Any gas that has a temperature, anything above absolute zero, is also emitting its own radiation. So it's not just a passive blocker, it's an active source, glowing with its own infrared energy, sending it out in every single direction. And last but not least, we have scattering. This is where the gas molecule doesn't eat the energy, it just smacks it. It knocks the radiation off its original path and sends it careening in a totally new direction. Seriously, think of a pinball machine. Scattering is what makes the path of energy so chaotic and incredibly hard to predict. Now, this might all sound a bit abstract, but here is a dramatic, real-world example of absorption in action. Way up in the stratosphere, molecules like CFCs float around. They end up absorbing super high-energy UV radiation from the sun. But instead of just warming up, the energy is so intense it literally rips the molecule apart. This unleashes a chlorine atom, which then goes on a rampage destroying ozone molecules. It is a perfect and frankly terrifying example of radiation interacting with a participating medium, our atmosphere, with massive consequences. Okay, so you've got all this absorbing, emitting, and scattering happening all at once. It's chaos. So how on earth do scientists and engineers figure out where all that energy actually goes? Well, this is where we have to try and decode the physics. The master key to all of this is a beast of a formula called the radiative transfer equation, or RTE for short. The best way to think of it is like a mathematical tug of war. On one side of the rope, you have energy being pulled out of a beam of radiation as it gets absorbed by the gas, and on the other side, you have energy being added in as the gas itself glows and emits its own radiation. Now, actually solving the full RTE is, well, it's brutally difficult. So, for many situations where absorption is really the main thing happening, engineers came up with this fantastic shortcut. They basically asked, what if we just ignore everything else for a second and only focus on absorption? The answer to that question is Beer's law, and it's so elegant. It just says that the strength of the radiation dies off exponentially the deeper it travels into the gas. To make life even easier, scientists took that idea from Beer's law and boiled it all down into one single, powerful number: optical depth. Honestly, the best way to think about it is just fogginess. A gas with a low optical depth, that's a crystal clear day. Radiation sails right on through. A gas with a high optical depth, that's a super dense fog. It's extremely good at blocking and absorbing radiation. All right, so now that we've got the basic physics down, let's zoom back out to the big picture. Why does spending all this time mastering this science even matter? Well, it turns out the applications are absolutely critical to our modern world. And this isn't some academic exercise. Not at all. This science is essential. We're talking about designing rocket engines that don't melt, building efficient power plants, trying to get nuclear fusion to work, creating crazy high-tech insulation, and, as we've already seen, building the climate models that help us understand the future of our own planet. I mean, just think about it. Inside a rocket engine, you have these incredibly hot gases. They are just blasting the engine walls with intense thermal radiation. If the engineers get their predictions of that heat load wrong, the engine could literally melt in midair.
And then, at the complete other end of the scale, the exact same physics applies to our planet. To understand and forecast something as huge as climate change, scientists have to be able to predict exactly how greenhouse gases absorb and re-radiate heat all over the globe. Same science, totally different scale.
Right, so up to now, we've kind of been pretending we're dealing with a single, simple gas. But the real world is messy. A combustion chamber or the Earth's atmosphere, they're not just one thing. They are complex cocktails of different gases all mixed together. And that brings up a really practical problem. How does an engineer deal with a real-world mess like the hot carbon dioxide and water vapor churning around inside a power plant? You can't sit there and solve the full radiative transfer equation for every single molecule. There has to be a better way. And for decades, the answer has been this really clever engineering tool. Instead of getting bogged down in pure theory, engineers ran a ton of experiments on gases like CO2 and water vapor. They took all that real-world data and compiled it into charts. So now, if an engineer knows the temperature, the pressures, and the basic shape of their system, which gives them something called the mean beam length, they can just go with a chart and look up the properties they need, like how well that gas mixture emits heat. It's like a cheat sheet. And that really brings our whole journey full circle, doesn't it? We started with the fundamental physics, absorption, emission, then we peeked at the complex math that describes it, and we ended up with these practical, data-driven charts that engineers use every day to build and understand the world around us. So this invisible dance of energy happening in what we think of as empty air is truly one of the most powerful forces shaping our technology and our entire planet. It really makes you wonder, right? What other invisible forces are out there, just waiting for us to figure out how to see them?